Welcome to day 5. We're going to be going over angular and linear velocity. So we have this scenario going on right here to kind of get us set up with what angular and linear velocity is talking about. So if you're on a merry-go-round and you sit on the outside versus if you sit a little bit closer to the center of the merry-go-round, you actually feel like you're going faster. And it's not just that you feel like you're going faster, you actually are traveling faster because you're traveling a further amount of distance. So if you think about circumferences of circles, you're traveling a bigger circumference if you're sitting on the outside of a circle versus closer to the center of the circle. And that describes linear velocity. At the same time, you're still rotating at the same speed no matter where you are, sitting either at the edge or at the closer. So this rotational speed we define as angular velocity. So the angular velocity of a point on a rotating object is basically measured in terms of some sort of angle measurement, so like radians or degrees, over time. Okay, so every single one of these is going to be in, nope, my board doesn't want to write. It's going to be some sort of angle measurement over time. Every single time. That's how you can recognize what angular velocity is. Linear velocity is measured in terms of a distance over time. So we have inches per second, meters per minute, feet per hour, miles per hour. So it's always some sort of distance measured over time. And that's the rate that you're really familiar with. So I have a little example here dealing with a tire. Try to connect angular and linear velocity. So if a tire has a radius of 11 inches and is traveling 35 miles per hour, we want to figure out what's going on here. So does the 35 miles per hour represent angular speed or linear speed? So since 35 miles per hour, that miles is a measure of distance, we know that this has to be a linear speed. So 35 miles per hour is talking about linear speed. It says, find the linear velocity of this tire in inches per second. So we already know it right now as 35 miles every 1 hour. So that's what 35 miles per hour means. And what we want to do is convert this into inches per second. So I'm going to focus on the time part first. So right now I have hours. I need to turn this into seconds. So the way I'm going to do that is what's called unit cancellation. So I have 1 hour is the same exact thing as 60 minutes. And 1 minute is the same exact thing as 60 seconds. And the reason that I am doing this is because now my units cancel. So hours cancels with hours, minutes cancels with minutes. And right now, if I were to multiply this all the way across, I would have 35 miles, okay, there's no other units on top, and divided by 3,600 seconds. So I have part of it now, I have seconds. I need to turn that miles now into inches. So I'll use another conversion. I'll say that there are 5,280 feet every 1 mile. And ultimately I'm trying to go to inches, so I'll do one more. I'll say there's 12 inches in every 1 foot. And again, I did this purposefully so that my units, miles now cancels with miles, feet now cancels with feet. And if I look at the top at all my units, I have miles, hours, minutes, and feet are all canceled, so the only one I have left is inches. And on the bottom, hours is canceled, minutes is canceled, seconds I still have, miles and feet are canceled. So when I just multiply straight across, I'm going to get my answer in inches per second. So 35 miles per hour is the same thing as 616 inches per second. So next it says find the angular velocity of this tire in revolutions per second. So I'm actually going to start off with the 616 inches per 1 second because now I already have my units of seconds. I need to try to find a way of converting inches into revolutions. And this is where we have our first little bit of trickery. I need to introduce a unit of revolutions, so 1 revolution, and there are 2 main things that can happen when you're talking about revolutions. You can either be talking about how many angle measurements it's going through, or you could talk about the distance it travels. So we're going to focus on distance because right now I have a measurement of inches and I want to cancel that out. So I'm going to do 1 revolution happens every circumference. So in this case, every 2 pi times 11 inches. Okay? my units of inches are going to cancel, and I'll be left with revolutions per second. So I just multiply straight across and reduce, and I got 28 pi revs per second. If we want to convert back and forth between angular and linear velocities, we're actually going to take a pit stop in revolutions, okay? So if I'm over here and I have angular and I want to convert to revolutions, there's something I'm going to do. And then if I wanted to convert revolutions into linear, there's something else I could do. And this works backwards. If I'm in linear, I could work backwards to revolutions and then forwards towards angular. And there's two ratios that we're going to use that will help us out. So on the linear side, we're going to focus on the circumference, which is measured in some sort of units, over one revolution. So we know that happens every time. Any circle you're in, one revolution is equal to one circumference, distance-wise. For angular, we can do 2 pi radians every one revolution. And this is also true. We could use 360 degrees or any sort of measurement. But we'll use these two facts to help us convert back and forth between linear and angular by first turning it into revolutions. And I'll do some examples of those in a little bit. Okay, so what I have now is just 3 different examples of the types of problems we're going to be working with in this chapter. So the first one I have here is with connected rotating objects. So an example of this that I have here, the picture, is gears on a bike. So the gears are connected by a chain, which means that they have to be traveling at the same linear speed, because if they weren't traveling at the same linear speed, one part of the chain would be moving faster than another part, and it would either bunch up or it would break apart because it wouldn't be traveling at the same speed. But the actual angle that's going on right here, so like this angle and this angle, those are different. So in this particular setup here, these types of objects have the same linear, but they have different angular velocities. So the linear speed of this circle is the same as the linear speed of this circle, and actually this little tiny one right here and this little tiny one right there, if there is one, I don't actually know. They all have the same linear speed, but they're all rotating at different speeds, okay? Because this one over here, the smaller one, it needs to be rotating faster than this one, because this has to go around more times than this one for it to travel the same amount of distance. Here we have analysis of a single rotating object. Okay, so an example of this is the merry-go-round or a Ferris wheel or any sort of thing like that, like a CD or a DVD. All of those, they have a very similar property as well. So if I have a circle right here and here's the center, they're all rotating at the same speed. So like this line right here would travel all the way around at the same angular speed. The measures are going to be the same. The angle, no matter where I am on this line, whether I'm right here, here, or anywhere in between, the angle's changing at the same speed. But it's not traveling the same speed or the same distance. So like this one only travels that far. This one is traveling that far, and so on. So since they're traveling a different distance, but they're doing it at the same angular speed, that means that they have different linear speeds. Okay, so this type of setup has the same angular, and this one has a different linear. And the last type we have down here is just a combination of these. So here I have a bicycle, okay, and we have lots of things going on here. So here I have the front wheel, there's the back wheel, here's the gears that are associated with the back wheel, here's the gears for the pedals, and then there's the actual pedals themselves, because they're traveling in a circle too as you're pedaling. So every single one of those, okay, are going to have the same angular speed. Okay, so same angular speed or velocity. Math people use that word interchangeably. Okay, but there are some differences now when it comes to linear speed. The two tires, or the wheels, they're going to have the same linear speed. They're propelling the bike forward, they're moving at the same distance, they're covering the same amount of ground over the same amount of time. And then the two gears, so the one that's attached to the wheel, right up here, and then the one that's attached to the pedals, those are going to have the same linear speed, just like in the first example. So those have the same linear speed as well. And we also have the pedals on there. They're doing different linear speeds, but they have the same angular speed. So we might have a problem that relates all of these together, where we're going to be changing things and trying to decide, hey, Do we have the same linear speed right now, or do we have the same angular speed? And then it might change depending on where we're at. So I could give you information on the front wheel, which you would have to then translate to the back wheel, which we could then move onto the back gear, and then we could take the back gear and move it to the pedal gear, and then move it all the way to the pedals. Okay, so that's the type of complex problems we might be dealing with. Okay, so I'm going to pause the video now, and I'm going to hopefully have a really cool demonstration of it if I can find one. That was so cool, right? I know, amazing. So what I'm going to do now is 2 examples for you. If you'd like to pause the videos, you're more than welcome to. Example 1 is going to be a connected rotating object. We have a large pulley, 120 millimeters in diameter. Okay, so we like to think of these more in terms of radiuses. So this is a radius of 60 millimeters, pulling a small pulley of 40 millimeters, so say that's a radius of 20. And they're being pulled by a belt, okay? And the smaller pulley has an angular velocity of 100 RPM, which we always assume, if it says RPM, that it's revolutions per minute, not radians, revolutions. First question says, what information is vital to analyze this motion? So we have to decide what is going on here. Do these 2 circles have the same angular or the same linear? Okay, and since they're connected by something, they're going to have the same linear speed. Now it asks us, what is the linear velocity of the smaller pulley's rim? What we'll do is we start off with the information they gave us, 100 revolutions per 1 minute. And what we need to do is turn this into a linear velocity, so that's a distance. Since I wasn't specified, or they didn't specify what distance to go for or what time to do it in, I'll try to do as little conversions as possible. So in order for me to convert out of linear, I'm going to turn this into revolution. So I want to introduce the units of revolution, so they're going to be on top. Whoopsies, messed up. I'll leave that in there for you, okay? Oh, now I got a fat marker. Everything's ruined. All right, so I want to cancel out revolutions. Sorry, so I need to put revolutions on the bottom. I need to introduce a distance. So I'm going to use the circumference. So in this case, I'm dealing with the smaller pulley, so I have to use the radius of the smaller pulley. Okay, my units of revolution are going to cancel. If I multiply this all the way out and simplify, I get 4,000 pi millimeters per minute. Okay, and this is a linear velocity, it's a distance over time of the smaller one. Now, since the smaller pulley and the larger pulley have the same linear velocity, the answer to the next question is very easy. It says, what is the linear velocity of the larger one? Well, it's the exact same thing. And here's where we get a little bit trickier. Now it wants to know, what is the angular motion of the larger pulley in radians per second? So right now I'm in linear. I'm going to need to convert to radians, and we're going to take a pit stop in revolutions. And that's the way that I like to think about it. So I'll be taking a pit stop in revolutions. I need to introduce that. I need to cancel out my distance now. I need to cancel out millimeters. And since I'm in the larger pulley, I'm going to use the larger pulley's circumference. So I'll have 2 pi 60 millimeters, because I need to use the radius of the larger pulley. Right now my units of millimeters cancel. I'm in revolutions per minute. I need to keep going with this. I'm going to convert it into radians now. So I'm going to do 2 pi radians, so that's 1 full time around the circle. It's the same as 1 revolution. So this was me taking my pit stop in revolutions. I'm now in radians per minute. It needs to be radians per second, so I just use 1 minute is equal to 60 seconds. Multiply all the way across, simplify, I get 10 pi over 9 radians per second. So I know the larger pulley is rotating at 10 pi over 9 radians per second. It has a linear speed of 4,000 pi. I know the smaller gear also has a linear velocity of 4,000 pi. It's spinning at 100 RPM, revs per minute. I don't know what its radians per minute are or radians per second, but we could find that if we wanted to. Example 2, which is numbered 1 as well, is going to be an example of a single rotating object. So here I have an example of one. This is called an LP, which thankfully is even too old for me to know officially what it is, but it's essentially just a record. And it says that it's rotating at 33 revs per minute. So what I want to do now is convert that into radians per second. And since I'm already in revolutions, I don't need to worry about any sort of really hard conversions. I'm just going to start off by writing what they gave me. And I'm going to convert it first into seconds because that's the easiest thing for me to do. So I do 1 minute every 60 seconds. Minutes cancel. I'm left with 33 revolutions every 60 seconds. And what I want to do now is cancel out revolutions. So I'm going to put it on the denominator so it'll cancel with the other revolutions and introduce radians. So 2 pi radians. Multiply straight across, simplify. I get 11 pi over 10 radians per second. Now it says find the angular and linear velocities of the record per second at the point at which the needle is located when it is just starting to play. So it starts all the way at the outside, which is 14.5 centimeters in the center. So I need to know what's going on with this particular example. And I know that it's rotating at the same speed no matter where I'm at. So its angular speed is still going to be 11 pi over 10 radians per second. I don't need to do any conversions for that. And its linear speed, I do need to do some sort of conversions for this. And it's actually easier for me to jump back to the original information I had, which was 33 revs per minute, than it is for me to deal with the radians per second. If I was in radians per second, I would need to take a pit stop at revolutions anyway in order to get to linear. So I'll do the first thing again, get rid of minutes and turn it into seconds because they asked me to turn it into seconds. And then I'm going to try to cancel out the units of revolution. So I put it on the denominator. I need a measure of distance, so I will use the circumference. Okay, so minutes cancels, revolutions cancels. I'm left with centimeters per second. That's the distance over time. Multiply it all the way out. I get 15.95 pi. Okay, or you could write it as a fraction. It doesn't really matter. So I have 319 pi over 20, and then we always include our units. Just find the angular and linear velocity per second at the center of the turntable now. So we already know the answer for angular. That's easy. It's exactly the same because it never changes in this setup. Linear we have to talk about a little bit, and it's a little bit confusing to think about, but it does not have a linear speed. We would say that it has none, okay? Or we could say that it's 0 or something along those lines, but basically we have a point, so here's a point, and it's rotating around, but like right now I could be rotating it and you can't even see it, and that's because it doesn't actually travel any distance. It just sits right in its place and rotates, turning around in a circle, never actually moving any distance. So it has no linear velocity if we're at the center. There you have it. That's the end of this video. Hope you like it. We'll practice some of these in class tomorrow. See you later. Bye.